Okay, we're going to talk about the Pythagorean Theorem right now. To start off with a couple bits of vocabulary, you start with a right triangle, which has two legs, as I'm showing here in red, which are the two shorter sides that are on the left and right, or either side of the right angle. And then across, you have the hypotenuse, which is the long side across from the right angle. Now in our formula, the two legs are going to be A and B. It doesn't matter which order. Either one can be A and either one can be B, since you're going to be adding them together. And the hypotenuse is always going to be C, and that's really important that you don't get that mixed up. Okay. Our formula, Pythagorean Theorem, which many of you have already seen before, is going to be A squared plus B squared equals C squared. Now we're going to go through a few examples, and after those examples, if you're interested, I will show a brief proof of the Pythagorean Theorem using some simple geometry and algebra. One more note before we go on to our first example is comparing exact numbers with approximate numbers or approximations. Our answers should all be given in exact numbers. Now if I asked you which of these two square root of 2 or 1.4142135 is an exact number and which is an approximation, I imagine a lot of you would say that this one is the exact number because it's got so many decimal places. It's got to be so specific and so detailed, when actually that is the approximation. The square root of 2 is an irrational number, and an irrational number, by definition, means that it is a never-ending decimal that goes on forever and ever and ever without any pattern. So anytime you write a decimal as an answer for a square root, you're actually approximating it, because this decimal keeps going. After 135, it keeps going 6, 2, 3, 7, and so on and so forth. Okay, so every answer I want you to give on this homework will either be a whole number like 3 or 5, or it will be given as a square root, something like the square root of 2. I do not want you to use a calculator to give decimal answers. There should be no decimal answers when we're dealing with the Pythagorean Theorem, because we want exact answers, not approximations. Okay? So next we're going to start with our first two pretty straightforward, easy examples. Now, just as a kind of table of contents for the examples we're going to go over one, which is a simple application where you just need to find the hypotenuse. You're given A and B, and you need to find C. Number 2 is the case where you're given one leg and the hypotenuse, and you need to find the other leg. So you're given A and C, and you need to find B. Number 3 comes back to the statement that if and only if it's a right triangle does the Pythagorean Theorem work. So we can actually check if a triangle is a right triangle by plugging that into A squared plus B squared equals C squared. And so we can actually answer the question, is this a right triangle? And that question might come up on the homework. So if it ever asks, is this a right triangle, you're often going to use the Pythagorean Theorem. Number 4 is a little harder. Obviously, it's not drawn to scale because those two x's look like they're different lengths. But this is the question where you're given just the hypotenuse and told the two legs are the same length, and you're asked to find that. And then 5 is an interesting one. It is when you are given very large numbers. There's actually a simpler, easier way to do it than multiplying out those large numbers and adding them together. Now I chose two really easy large numbers, 300 and 400, rather than being some odd, 371 or something like that. And then finally at the end I'm going to show a brief proof for those of you who are interested in how to prove that the Pythagorean Theorem is true and how to prove that it works. The first example is when you're given the two legs of a triangle and you're asked to find the hypotenuse. Now, in this case, I made it so the number would work out nicely. On the next example, I will purposely make it so the answer comes out to be a square root and does not come out to be a whole number. Okay, so to set this up with a squared plus b squared equals c squared, we know that our hypotenuse is across from our right angle and is our longest side, so that is going to be our x squared, and the two legs next to our right angle are our legs, and so those are our a and b, so let's say 6 squared plus 8 squared. Now we can go through and do 6 squared, which is 6 times 6, or 36, plus 8 times 8, which is 64, is equal to x squared. So that means that 100 is equal to x squared, which means if we take the square root of both sides, we get that x is equal to, I'm just switching the sides here now, but x is equal to 10, because 10 times 10 is 100. Okay, and the next example, which is the other version of the simplest application of the Pythagorean theorem, you've given one leg and the hypotenuse, and you're asked to find the other leg. Again, this is a straightforward application. So we know across from the right angle is the hypotenuse. So we know when we have a squared plus b squared equals c squared, that our c here is going to be 6 squared. And then we know our two legs are going to be x and 5 because they're next to our right angle. And so we have x squared plus 5 squared equals 6 squared. And I purposely made it so this one wouldn't work out and our answer would be left as a square root. So this is going to be x squared plus, and again 5 squared means 5 times 5, so that's 25, equals 6 times 6, which is 36. Now to solve this, just as if we were solving for x on any problem on a weekly quiz, we subtract 25 from both sides, and we get x squared equals, because this is gone, equal to 11. Now we take the square root of both sides to undo that x squared, and what we get is x is equal to the square root of 11. And that's how we leave it. You could punch that into a calculator to get the decimal approximation, but we want for our answers the exact answer. And square root of 11 represents that never-ending, beautiful, no pattern to it number, that irrational number. Okay, now for our third example, we're given all the sides of a triangle, and we're asked if the triangle is a right triangle. Now, to test this, we're going to use the Pythagorean theorem. If it works out that a squared plus b squared is equal to c squared, then that means this must be a right triangle. Now, if a squared plus b squared are longer or larger than c squared, it is not a right triangle. If they're smaller, it's not a right triangle. If and only if a squared plus b squared equals c squared works out, then we know this is a right triangle. So let's test it right now. Okay, we've got a, which is our first leg, and b, our second leg. So we've got 5 squared plus 12 squared to plug in, equals, and then we've got our hypotenuse across from our possible right angle. And if you weren't given which side is the right angle or which angle they're checking, you know always that the largest number, this 13, which is the largest number, has to be our c. Okay, so you've got now 5 times 5, which is 25, plus 12 times 12, which is 144, equals 13 times 13, which is 169. So we add 25 to 144, and we get, that's 160, and then 5 plus 9, or 5 plus 4 is 9, so we get 169 equals 169. Now in this case, it did work out that 169 is 169, so the Pythagorean theorem in this triangle works, so the answer would be yes. This is a right triangle. Okay, now the problems start to get a little more challenging, not too bad. In this case, we're told that the two legs are the same, So they're both equal to x, and then we're given the hypotenuse is 12. So let's go into our Pythagorean theorem. We've got our A and our B next to the right angle. So those are our two legs. And so we've got a squared plus b squared equals c squared. And so we've got x squared plus, again, x squared equals. And then we've got our hypotenuse across from the right angle, our longest side, and that's 12 squared. Now, what we're going to get is x squared stays as x squared plus x squared equals, and then 12 times 12 is 144. And now we're going to try and solve this. So just like as if you were adding 3x plus 5x, you're saying, okay, I've got 3 of these x's, and I'm adding together 5 more x's. So I can combine what we call like terms and get 8x. Well, same thing over here. I've got one x squared, and I've got another x squared. If I combine these two, it's like saying I've got an orange over here and an orange over here, and I'm adding them together. So I've got 2 of these x squareds, and those are equal to 144. Okay? So I can go ahead and divide that by 2 and get, okay, x squared is equal to 72. All right? And now, of course, I just take the square root of both sides to get rid of that x squared, and I get x is equal to square root of 72. You don't need to go any further. You can just leave it as a square root. Okay, now looking at this problem right away, especially if those numbers weren't so nice and even, like 300 and 400, if they were some sloppy numbers, 582 and 316. I would be pretty scared too on a quiz, not allowed to use a calculator, that this would be pretty difficult. Now actually there's a nice trick to make this a whole lot easier, okay? And it's having to do with similar triangles. What we can do is say this triangle is similar to a smaller triangle. Now, if we look at 300 and we look at 400, what do those two numbers have in common? In other words, say if that was a fraction, what could we reduce those two numbers by? And now, obviously, we could reduce them both by 100, 300 and 400, right? So we can say that this big triangle is 100 times as big as a little tiny triangle that is 3 by 4, still a right triangle. And now across from it, instead of using the letter X so I don't get confused, I'm going to use a letter, say, M, okay? And so what we're going to do is we're going to solve the Pythagorean theorem in this smaller triangle for M, and then we're going to multiply it by 100 because this bigger triangle is 100 times this smaller one, okay? So we're going to use our Pythagorean theorem. We're going to use our first leg A, our second leg B, and so we're going to get a squared plus b squared equals c squared, and our a and our b are going to be 3 squared plus 4 squared equals, and our hypotenuse across from the right angle, our longest side is m, so equals m squared. And so what we get is 9 plus 16 equals m squared. In other words, let me just make this a little smaller so we can work with it. We're going to get 25 equals m squared. And when we take the square root of both sides, we get, just switching the sides here, that m is equal to 5. Okay? So now what we can do is we can say, okay, well, if m equals 5, then 100 times 5 means that x is equal to 500. Okay, and that's because we use that similar triangle. So if we know there's a triangle that's 3, 4, and 5, and this other triangle is 100 times that big, then we know this triangle is 300 by 400 by 500. And that's an easy way to deal with big numbers when dealing with Pythagorean theorem. Okay, now this proof of Pythagorean theorem is pretty straightforward. You just need to know how to find the area of a triangle and the area of a square. And then we're just going to be subtracting some areas and trying to find out if this is true. So we're going to start with this triangle. And now forgive my drawing skills. Okay, so we've got A, B, and C. We're going to put another triangle on top, that is A, B, and C. Then we're going to put another triangle to the side of that one, that is again A, B, and C. Whoops, that's C there. Undo that. Okay, and then we've got another triangle here, that is A, B, and C. And now with a little bit of arithmetic with these angles, you could find out actually that these inside angles are right angles. So what we get is we get a large square with sides A plus B and A plus B. And then we get a large square on the inside, or a slightly smaller square, with side C. Okay? And what we're going to try and do is figure out the area of this shaded region in two different ways. Okay? So one way we can find that out is we can say, okay, well, the area of the red shaded region is 4 times the area of the triangle. Right, this A, B, C, okay? And we're going to say that's equal to the area of the really big square, that's A plus B and A plus B, minus the smaller square, that is C by C, right? No one would argue that that's true. We could find the area by adding up the 4 red triangles, or we could find the area by taking the big square and subtracting the small square, okay? So what I'm going to do now is just shrink this down so we have a little more room to work. Okay, so 4 times the area of that triangle. Well, the area of a triangle is 1/2 base times height. So we have 4 times 1/2. The base times the height, so that's A is the base times the height is B, is equal to the area of this triangle, or this square, which is A plus B times A plus B, minus C times C, or C squared. Okay? Now again, I'm just going to shrink this and get it out of the way for us, okay? So what we're going to get here is 4 times 1/2 is 2AB equals, and we're going to FOIL this with a little arithmetic. It is A squared plus 2AB plus B squared minus C squared. And now all I'm going to do is add this, let's do it in red, I'm going to add C squared to both sides to move it over to the left, and I'm going to subtract 2AB so that it disappears from both sides. And now the C squared is gone, and look at what we've got on the left is C squared is equal to A squared plus B squared. It's a nice, simple, short little proof of Pythagorean theorem. Now we skipped over a lot of parts where we're proving that the inside part is a square, it's got 4 right angles and all that. But it's a pretty elegant proof, and you can find similar proofs online if you're interested.